Here's the tutorial for continuous variables. So we're going to walk through creating a change score. We'll look at a two-group t-test. We'll look at correlation between two variables. And we'll look at an ANOVA, or an analysis of variance, where we have multiple groups. So first, let's think about creating a change score. You can see here in this data, the means tutorial data, we have 480 subjects, participants, and we have a pre and post score. To create a change score, you want to create a new column, which you can do in the columns menu, add column or new column, or you can simply double click over on the right side and create this new column. I'm going to double click again to get the column information to come up. You could also have gotten it to come up here in the columns menu. I'm going to call this change, and I'm going to note that is pre or is post minus pre. It's very helpful if you name your variables so that when you're looking at them you remember. Under column properties here I'm going to say formula, and then I'd like to edit the formula. Once you're in the formula box, you'll notice that there's no formula at the moment here, and what we would like to do is do post minus pre. So what we'll want to do here under the columns is select post, and you'll see it's put it down here in the formula box, minus pre. So this is post minus pre, such that if post is larger than pre, you will get a positive score. If pre is larger than post, you'll get a negative score. Now with this particular data, I can tell you that everyone has seen an increase, so we will only see increases in scores. And I want to press apply. If there are any errors, they would pop up now, but seeing none, I'm going to press OK, and I'm going to press OK again. And you can see change pre-post. Now, the first thing you'll want to do is do a distribution of all three of your variables to make sure that you've calculated your formula correctly. So you can see here that our pre-scores range from 0 to 6, and our post scores range from 1 to 15. Therefore, we should have almost all positive values, one would think. We can see here that we have at least one negative value. Our minimum value is a -1. So what I would want to do is to select the row that is the -1, which is right here, and go back to the table. There are actually two rows that are -1. There's a couple of different things that you can do. You can do a subset, since those rows are selected, or you can go down here to select, oh, excuse me, that did not work. In the Windows side, you can select it straight from there. You have to, excuse me, I'm in the Mac side here. So I'm going to show you the third way that you can do is row selection. And I want to select where, and I want to select where change post minus pre is less than 0. So I want to find the negative scores. Change post minus pre is less than 0. I'm going to add that condition. Change post minus pre is less than 0, and press OK. And again, you can see there are two rows selected. I'm going to go ahead and do tables, subset, and press OK. And it will bring up these two rows. You can see my pre-score is 2 and my post score is 1. In this particular data set, the scores can only have increased, so this is an error. These are errors with a -1. In this situation, you would need to go validate the data. If you can't validate it knowing the data setup, our choice here is to exclude those. I'm not going to save the subset. Since I already have these selected, I want to exclude them from my data. And if I were writing this up as an analysis, you would need to make sure that the exclusion criteria were complete and validated data, and maybe include that 2 were deleted for possible, because the resulting endpoint was not a possible value. So now that I have them selected, I still have the 2 selected, I'm going to go back to the rows menu and press exclude, unexclude. And you'll see now down here that I have 2 rows excluded. And so if I do my distribution again, my pre post and change pre-post and press OK. You can see now that my change here runs from 0 to 9. So you can't get worse pre to post, you can't go down pre to post. You can only stay the same or increase. And we see that in the change score. You've also noted that there are now only 478 people. So we're ready to proceed here. To assess the change score, we'll want to go ahead and do a distribution just on change. Press OK. And so the question is, has there been an increase? So is our change score different from 0? So we want to know if it changed post-pre. So remember, people can only stay the same or their score can go higher. The question is, did it? So under the red drop down here, there's a couple of things that you want to look at. We want to look at the normal quantile plot and see if it's normally distributed. In this case, it doesn't look to be normally distributed. We would like to see this straight line. If it were normally distributed, to test, if it were 0, you would want to test the mean. And you would test this hypothesized mean. If you knew the standard deviation, you could enter it here and get a z-test. We very rarely know that. So if all you wanted was a t-test, you would just press OK. And it would give you the t-test, and it would give you the options for the p-value. If you're unsure which one to choose, click on the question mark here, and then you can click here, and it will bring up the details on testing the mean. Because we know that we have a not normally distributed variable here, we're in a situation where we need to do a wilcoxon test. So under test mean, it'll bring up that same box. We just want to check wilcoxon signed rank. This is going to test if the median is 0, and press OK. And again, here, the signed rank, we get the p-values associated with the signed ranked score. So in this situation, the two-sided p-value is this first one. Our one-sided testing, if it's greater than 0, is here. Our one-sided testing, if it's less than 0, is here. And obviously, because our observed statistic is greater than 0, our actual change was 0.72, we would never be able to declare that the change was less than 0. So that's why the p-value here says 1. For testing, if it's greater than 0, it's a less than 0.0001, or testing a two-sided, it's less than 0.001. So you can see here that I've stopped moving the cursor, and it gives you an interpretation, and you can find that and jump with any number of the statistical tests. So that is how to test a single mean. Up next, we want to look at a two-group t-test. So let's say our question is there a difference between the ages for the males and females? So I'd go into Analyze, and first, of course, you want to look at gender and age. From here, you can see that we are largely female. That's okay. And there are 478 genders given. And we can see that our age runs from 18 to 61 with a mean of 37. It looks relatively unimodal here, or one normally distributed variable. Now we can go ahead and do a normal quantile plot on that. So age looks relatively normally distributed. In large sample sizes, that's pretty common. There's maybe a slight S shape here, but you can see that all of our points are within, for the most part, these confidence bounds, and we have a very large sample size. So I'm comfortable with normality on age. It doesn't look like we have any missing variables or anything very odd that we need to be concerned about. So from here, we'll go ahead and do the t-test. Under Analyze, that is fit y by x. We are going to put our gender here under x, and our age here in y. You can see down here that with an x variable that is a red histogram and a y variable that is a blue, we're going to be in the one-way analysis of variance situation. But because we only have two groups, it's just a simple t-test. We'll press OK. And it brings us up this very straightforward plot that you'll get used to seeing for the rest of 611 and 612. Right now you can see that all the points are standard in a line. This doesn't tell us how many points really there are, because anybody that had the same age, 25, would be right on top of anyone else. You can also see that female is given a larger portion of the x-axis. That's because we have more females. If you'd like to change that, which you would need to change if you were displaying this in a paper or on a slide or in any presentation of results, you would go ahead and unclick x-axis proportional, and you can see now that they're the same, given the same amount of width on the y or on the x-axis. Under display options again, I may want to see points jittered, and then you can sort of see how many duplicates we have. The gray bar here is now telling us where the average mean is. In order to test whether or not we have normality within the groups, do a normal quantile plot here, make that larger, and these look all right. In addition, remember, these lines will tell you if they're parallel, that the variances are equal. If they're not parallel, you need to be concerned about variance. In addition to that, remember, if you have unequal sample sizes, which we do, we have way more females than males, we might be concerned with unequal variance. So we seem to be okay with normality. The variance actually these look relatively parallel, but because we have unequal sample sizes, we may want to test that. So let's go up here. We can do a couple of different things. If we'd like to start with getting some summary statistics, we can look at the quantiles. That will bring you up your box plot. And again, these actually look like they're relatively similar. If you have questions about the box plot, click on the question mark and click in here, and it will bring up the help section. We can see from the quantiles, we know that we range from 18 to 61. So our minimum overall and our maximum overall are within the females. Not surprising, we had more data with females. The medians seem to be only 1 year apart. And then the other percentiles seem to be relatively close. So might be trending a little bit younger in the females, but of course we haven't done a test for that yet. We can look at the means and standard deviations per group, and you can see that we have 345 females, 133 males. Our means are pretty close to our medians in both genders, and our standard deviations are actually pretty similar. I would not be concerned about unequal variance here. If you are, then you can do the unequal variance test. Remember, we look at Brown-Forsyth. Remember that the null hypothesis is equal variance. The alternative hypothesis is unequal variance. Here we would fail to reject and stick with the null of equal variance. And again, JMP will give you instructions here. It's not significant at all, and this could be by happenstance, so it looks like we have equal variance here. So I'm going to go ahead and hide this. Our next step would be to do a means ANOVA pooled t, or you could just simply select the t-test. Because we only have 2 levels, these will give us the same result. Up here you will get the f-test as well, so I'll click on the t-test, and it gives you the distribution of what the t would look like, and it gives you your red line of where your difference is, gives you your t, gives you your 3 p-values depending upon your hypothesis. It also gives you your confidence interval on the difference. So our difference in age is less than 1 year, and we're 95% confident that it would range from smaller than a year to almost 3 years. So you can see that they've told you it's male minus female. You know that the males are older, and so it's telling us that there is no difference. But it could range as much as males being 1 year younger up to 3 years older. No difference according to the t-test. Again, you could also use means ANOVA pooled t. Here you'll start to see the analysis of variance, where we have the t-test, which we just saw, but we also have the f ratio. But what you can notice here is that the p-value for the t is the same as the p-value for the f. With 2 groups, the f and the t give you identical results, because it turns out that the t is just the square root of the f. And so you get the same p-value here. It gives you your means and standard errors. Not surprised to see the standard error of females being smaller, because remember, the standard error is the standard deviation divided by the square root of n. Since we have a larger female sample size, our standard error will be smaller. You also, in the means and standard deviations report, will get the confidence bounds for the males and females, and we can see that they overlap. So again, more evidence that they are not statistically significantly different. If we were not comfortable with normality or simply wanted to test the medians, then we could go up into non-parametric and do a wilcoxon test. And that will appear all the way down at the bottom. And again, not statistically significantly different. You would never report these scores for the score sum or expected. Those change with every different sample size. So all you would report here is the two-sided p-value. If you're doing a one-sided test, it's the p-value divided by 2. So for the greater than or the less than, but you need to change your difference. But it's just the p-value divided by 2 for the one-sided test. So that's it for a two-group comparison. What about our continuous covariates if we wanted to, or continuous measures if we wanted to look at correlation? Here we can look at age and weight, or we could look at age and BMI, or weight and BMI. In this case, we have not looked at weight or BMI yet, so let's go ahead and do a distribution on those. And they look okay. We've got a lowest weight of 94 with a high weight of 354. Lowest BMI, which is actually underweight, 17.2, and the highest of 58, which is in the obese range. But seems to be sort of skewed here on the weight and a little bit skewed on BMI. Let's go ahead, but doesn't look like we have anything that's very odd. Let's go ahead and do a fit y by x. Age, we're going to do weight. Let's look at weight by BMI. Press OK. And it brings up our scatter plot. So remember, what we are looking for here in the scatter plot is no obvious curvature, because then it wouldn't be a linear model. This looks like we could have a line fit, or that there could be a strong positive correlation between weight and BMI. A couple of things that you might want to do here would be to change the aspect ratio. And all I've done here is I've right-clicked, or in a Mac, control-click, and you can change the size and scale. I will go straight to frame size because I want to make it square. So let's do 400 by 400. This is going to provide equal distance for the axes, so the equal amount of space, make it a square graph. There's a couple of other things that you could do. If I wanted to change my marker size to make it large or a little bit easier to see, you could change the type of marker you have. All of those things can be done by right-clicking. You could change the background color if you needed to. For some reason, you could change a border. There's some other options you could do if you wanted to label some of the rows. One of the things you could do is to, if I wanted to label the rows, I can go back into the data, into the rows menu. Oh, sorry, it's not going to let me because I'm in the middle of the graph. So we'll show that in a second. So here, what we want to look at is we want to know if there is a relationship between weight and BMI. In the fit y by x option, you want to fit line, or you can do for correlation the density ellipse. To simply get the correlation, we're going to check the 95% density ellipse. This is somewhat like a normal quantile plot. If these are what's called bivariately normal, so they're moving in a normal manner together, 95% of the data will be within this circle, and it actually looks pretty close to that. And you can uncheck this little arrow here, and it will show you the correlation. So it's telling us that these are strongly positively correlated, a correlation of 0.8, which means as weight gets bigger, BMI gets bigger. You can tell it's a strong positive relationship because it is very steep here. There's only a few instances, some over here and maybe a few over here, that really aren't on this general line here. This p-value tells you that the correlation is statistically significantly different from 0, so these are positively correlated. If you wanted a simple line fit to get some prediction, you could do fit line. And you see here these, if it went corner to corner, from down here all the way up to here, that would be almost a perfect correlation. And that's why we have it as a square axis. So these being the same, you would know that this top to bottom to top corner would be a correlation of 1. We're slightly lower than a correlation of 1 here at our 0.8, but our linear fit model now gives us an equation. So we know from here, if you remember back to y equals mx plus b, your intercept, 5.68, plus your rise over run for your weight. This tells us that for every weight increase, we're going to go up 0.1 in BMI. That's what this estimate here in the linear fit line tells us. What you'll notice here is that the p-value for the f-test is the same as for the correlation. That will always be true. The p-value for your line fit in a simple linear fit like this with one x and one y will be the same as the correlation. So you'll notice that. In this case, we would conclude that weight and BMI are strongly positively correlated with a correlation of 0.9, which is statistically significantly different from 0. You could also look and conclude that for every 1 pound increase in weight, BMI will increase by 0.1. That is correlation. There's another way to get correlation actually under Analyze, under multivariate models, and under multivariate. You can put both weight and BMI in the Y column and press OK. And it again will give you the correlation up here. These are the same plot actually. So this has BMI on the X and weight on the Y, and this has weight on the X and BMI on the Y. So you can look at it either way. And then the options for here is that you can do the pairwise correlations. And again, it's going to give you the correlation and the p-value for that. Tells you the same thing. Okay, now what about on to our last topic in this area, which is the analysis of variance. So more than 2 groups. In this case, the only variable we haven't looked yet is race, so let's do that. And in this case, we have 3 groups of race, largely Caucasian. Then we also have African Americans, and we have some others. In this situation, again, fit y by x. We're going to put race as the x. And let's go ahead and do our BMI y and press OK. And again, because Caucasian has so much of the sample size, we're unequal. I'm going to go ahead and under display options, change to x-axis proportional. I'm going to go ahead and do my points jittered. And then in this situation, because we do have unbalanced sample size, we will want to look at our normal quantile plot. And in terms of normality, they actually look all right. They're in relatively sort of straight lines here. They would be within the confidence bounds for sure. In terms of assessing equal variance, they look relatively parallel, with the exception of right down here where they're crossing, but we know we have unequal sample sizes. At this point, you can simply do a wilcoxon. It's non-parametric. We can test the medians. Are they different? Yes, no. It's telling us yes. You'd want to report the quantiles here with the median BMI per group and say that they are different. So it looks like African Americans have a higher BMI compared to Caucasians and other races, or higher median BMI. This actually is not surprising given evidence that we know about weight and race, or BMI and race in general. Okay, so let's say we're okay with normality, but we're worried about unequal variance. So we can test them. Remember, our null hypothesis is equal variance. Our alternative is unequal. Brown Forsyth is telling us we have equal variance. If this was small and we decided we had unequal variance, we would report the Welsh F test, which would just be telling us that there is a difference in the mean weight here. Which reminds me, we need to actually look at our means and standard deviations, which are right here. Our standard deviations actually look fairly good, which is why we failed to reject in favor of equal variance. And if we decided that we were okay with normality and we're okay with equal variance, and we simply wanted to do a means ANOVA, notice that the /t test has disappeared here because we have more than two groups. You'll only see the /t in this fit y by x if you have two groups. More than two groups, it's going to say means ANOVA. Press the means ANOVA, and you'll get your one-way analysis of variance fit, 478 observations. The R-squared's not great, so we're not getting a lot of value out of BMI and race in general, but what our ANOVA table tells us is our hypothesis of equal mean BMI is rejected. We are going to conclude that we have unequal mean BMIs. The follow-up question should be, okay, where is that difference? You can look at the confidence intervals to determine that difference, or you can do compare means, and we would want to do a Tukey's comparison. Press OK, and you can see we get the Tukey's bars, or the Tukey's circles over here, and I can click on them, and it's telling me that Caucasian and other are the same. It's telling me African American and Caucasian are the same, and it's telling me that other is the same as everyone else. You might say, wait, what? I don't understand. The analysis of variance is telling us we have a mean difference in the races. However, when we go down here to look at the Tukey's, all the way down on the bottom, we can see that the only difference we're able to statistically significantly detect is that African Americans have a higher mean BMI than the other race. And that's a p-value 0.043. Otherwise, we're failing to detect a difference. This is due likely to the small sample sizes in our African American and other races. Our Caucasian is so large that it's going to be difficult to overcome the sample size difference. What we can conclusively say here is there is a difference in mean races between African Americans, Caucasians, and others, with a statistically significant difference between African American and other. You would then report the means, the standard deviations, the confidence bounds. You could report the confidence bounds on the difference, saying that African Americans on average have a higher BMI of 4.3 compared to other races. That's statistically significantly different. The difference of 2.5 between African Americans and Caucasians is not, and the difference of 1.8 between Caucasians and other races is not statistically significant, and those would be due to Tukey's HSD. So that pretty much sums up what you can do with a single x and a single y, where your y is continuous and your x is either categorical, like it is here for a t-test or ANOVA, or your x is continuous, where you would be looking at correlation or simple linear regression.